Yeah, hello. In my last class, I told you some of the very important applications of power electronics and some of the significant events in the history of power electronics till 1957, the year in which silicon controlled rectifier or thyristor was invented. As I go along the course, I will tell you the other significant events. Then we started discussing about the power semiconductor devices. I told you that power semiconductor devices are heart and soul of power electronic equipment. These are used as switches. Okay. That means either if when they are on, we need to operate them in saturation, and when they are off, we need to operate in when they are off, they are in cutoff mode. Only there are three types of switches. One is an uncontrolled switch. Uncontrolled because whether the switch is on or off, it depends on the circuit operating conditions. Say diode, for example. Okay. And there is a semi-controlled switch. A silicon controlled rectifier or a thyristor is a semi-controlled switch because it can be turned on by supplying some current to the gate or to the control terminal. Okay. But then, having turned on the device, you cannot turn it off using the gate. Now, the SCR which is conducting, which turns off, depending upon the circuit condition. If the current becomes 0 in the circuit, thyristor will turn off. Okay. And third one is a controlled switch. It can either turn it on or off using the control terminal. A bipolar junction transistor. By supplying a base current, you can turn it on. You make IB is equal to 0, base current 0, transistor turns off. Okay. Now we will study the various devices in detail. Yeah. First one is the diode. It is a two-terminal device. All of us know, we have been studying maybe since the class 11. Okay. Anode and cathode. So if VAK, voltage across the thyristor, the diode VAK should be positive, then it is said to be in forward bias mode and diode starts conducting. So for a silicon diode, a low power diode, it could be VAK could be of the order of 0.7 volts or so, and this value increases as the power rating increases. Say for a power diode, it could be of the order of say 1.5 volts or so. And when the diode is on, all of us know that current in the circuit is limited by the load. Okay. See, the ideal characteristics are along the y-axis, that's it can carry any current, assuming which is less than the rated, and it can block a negative voltage. Okay. It cannot block the positive voltage. Okay. And these are the characteristics of a non-ideal diode. Maybe a cut-in voltage somewhere at this point, and this is the current that is limited by the load. Okay. This is forward biased, and this is during reverse bias mode. VAK is negative. Okay. as long as the applied voltage is less than VBD, see VBD is this point, breakdown, junction breakdown. Okay. Diode will block that voltage. In other words, the maximum reverse voltage that is applied across the diode should be less than VBD. You need to ensure that. Say the input voltage is 230 volts, so negative peak is going to be 230 into root 2. So the voltage rating of the diode should be higher than 230 into root 2 if you are using in a single phase circuit, assuming that load is a passive one. Okay. Now, but then if the applied voltage is higher than VBD, and if you are not able to control the current that is flowing, then the device will get damaged. Remember. Okay. If the applied voltage is higher than VBD, and if you are not able to control the current that is flowing to the diode, it's going to be destructive. It's going to be destructive. Okay. So during on state, there is a finite voltage drop across the diode. I will call it as Vf, and Ia is the current that is flowing through the diode. So on state loss or the conduction loss is given by Vf into Ia. Okay. Now depending upon Vf and Ia, the magnitude of Vf and Ia, say if it is higher than a certain value, you need to go in for, or you need to mount the diode on a heat sink. Okay, invariably power diodes are mounted on a heat sink. A small signal diode you don't need to, or generally is not mounted on a heat sink. Okay. Now, all of us know the on state behavior of the diode. Now, in the power electronic circuit, the off state, the diode, the way it is turns off is a bit important. Why so? I will tell you. See, when the current in the circuit, of course this is the current that is flowing in the circuit, depending on the input voltage or so, current starts following. Okay. At this point, current becomes 0, but then diode continues to conduct. A reverse current starts flowing. A reverse current starts flowing till say TRR. Okay. That's because the minority carriers, they require a certain time to recombine with the opposite charge and to get neutralized. Okay. I'll repeat, the minority carriers which are there, they require a certain time to recombine. Okay. And that takes place in this time TRR. TRR is the reverse recovery time. Reverse recovery time. Okay. It is equal to as the time from this point, the first zero crossing to say 25% of the maximum value of the current that is flowing in the reverse direction. Say maximum value of the current in the reverse direction is IRR. Okay. So TRR is the time from this point to say 0.25 of IRR. I am assuming that this point is 0.25 of RR, and this current is the leakage current, which is very small, the leakage current. Okay. And this is the charge, reverse recovery charge. Okay. Now, what is the reverse recovery charge? It is the area of this plot. Okay. I am assuming that this is a linear one. I am assuming I am just determining the area of the triangle to find out the reverse recovery charge. Okay. The area of this shaded part is nothing but IRR, the peak, into TRR divided by 2. I am assuming that this is to be a triangle one, okay, area of the triangle. So, reverse recovery time and reverse recovery charge, they are very important parameters, two important parameters. Okay. Why are they important? See, even the current has become 0, it continues to conduct for goes to offset only after TRR. So, if the circuit in which the frequency of operation is very high, this TRR will play an important role, or in other words, TRR will determine the upper frequency of operation. Okay. And this QRR, or the reverse recovery current, it is flowing in the opposite direction. It is flowing from cathode to anode. Okay. So, this current is flowing from cathode to anode. So, either it has to flow to the source, or it may have to flow through other switches. Those switches have their own current carrying capacity. So, in addition to the load current, that device may have to carry this reverse recovery current. Okay. See, yesterday I showed you this power module. I said there are two control switches. The name of the switches I will tell you sometime later, and in parallel there are two diodes. These are the two diodes this module has. Okay. The current rating of this each diode is 75 amperes, and it can block 1200 volts. The reverse recovery time of this diode is of the order of say 0.2 microsecond. That is what the specification or the data sheet says. Okay. So, it could be of the order of 0.2 microsecond, and depending upon the junction temperature, QRR, the reverse recovery charge, is of the order of 1 microcoulomb. 1 microcoulomb. Okay. It is all given in the data sheets. Okay. So, what about the other ratings, important ratings of the diode? Now, what are the other important specifications of the diode? They are, one is average forward current. See here, it is required to assess the suitability with the power circuit. So, depending upon the input voltage, the load and the duty cycle, so average current can be determined. I am saying duty cycle because diode may not conduct for the entire cycle. The second point, reverse blocking voltage. The reverse voltage that is appearing across the diode should be less than the breakdown voltage. Okay. Third, on-state voltage drop. It is required to determine the conduction loss and therefore the heat sink size or the cooling requirement. The fourth one, TRR, reverse recovery time of the diode, is another very important factor in the diode used in high switching applications, or it is required to assess the high frequency switching capability. And the fifth one, the surge current rating. And to explain this, consider this circuit. What I have done is, there is a AC sinusoidal source, diode, I am connecting a switch and a capacitor. The remaining part I have not drawn. Okay. Assume that capacitor is completely discharged, okay, and I will close the switch at omega t is equal to pi by 2. At omega t is equal to pi by 2, input voltage is at the positive peak. Okay. Capacitor voltage is 0 and it cannot change instantaneously. So what happens when I close the switch? There is going to be a large inrush current. Why? Input is at the positive peak, at the output voltage is 0, and that large inrush current has to flow through the diode and it has to withstand that current. Okay. And let me tell you, this surge current is much higher compared to the average forward current. Okay. Maybe sometime later I will show you a data sheet wherein there is an average forward current, RMS current and surge current ratings are given. And next one is I square T rating, current squared time rating. Okay. It is an indication of, or it is the short term surge energy that the diode can withstand. Okay. This is required to choose a suitable fuse in the diode circuit. Okay. Now when this is important, so take this example. Okay, I have an input AC source, a diode and a capacitor. Now I have not drawn the remaining part of the circuit and I have a switch here, something that maybe an main switch also. Assume that I am closing the switch at omega t is equal to pi by 2 or in the positive peak. Okay. Capacitor is totally discharged. Okay. So in other words, there is a short circuit here. Capacitor voltage cannot change instantaneously. Voltage at this point is instantaneous value is at the peak and you have closed the switch at that time. What happens? A large surge current will flow because voltage at this point cannot, voltage across the capacitor cannot change instantaneously. Okay, it was 0 just prior to closing the switch. Okay, this is at the peak. You have closed the switch. A large surge current will flow. Okay, and diode should be able to withstand this surge current. Okay, which is higher than the average current rating. Okay. So that's about the diodes, the so-called uncontrolled switch. Now what are the various types of diodes? Okay. The first one is a rectifier diode or a slow diode. They are suitable for line frequency application. Say you want to rectify the input AC, which is 50 hertz. Okay. So you can use the conventional slow diodes or rectifier diodes. The reverse recovery time is generally not specified. They are basically slow diodes. So the maximum rating is of the order of 6 kV. The diode can block as high as 6 kV and current rating is of the order of 4500 amperes are available. Okay. I will repeat, diode which can carry say 4500 amperes of current and can block 6 kV, they are available. These are conventional rectifier diodes or slow diodes. There is a second type. The one is known as the fast recovery diodes. Fast recovery diodes. These are generally used in high frequency application. Okay. Sometime later in the course we will find that fast recovery diode should be used in the circuit. You cannot use the conventional rectifier diodes. So the rating is of the order of say 6 kV and current of the order of 1.1 kiloampere. They are available, okay, in the market. 6 kV can block, current rating is 1.1 kiloamperes, and the reverse recovery time could be of the order of say 0.1 microsecond. Okay. Could be. I am not saying that 6 kV 1.1 kilo diode has a reverse recovery time of 1.1 microsecond. No, the reverse recovery time of a fast recovery diode could be of the order of say 0.1 microsecond. The just now example which I showed you is of the order of 0.2 microseconds. Okay. The third one is the Schottky diodes. Okay. What are the features? They have a very low on-state voltage drop. Very low on-state voltage drop. Basically, these are only majority carriers. Current only due to majority carriers. Okay. But then the voltage rating is low. Maximum voltage rating is of the order of 100 volts or so, and current is of the order of 300 amperes. And the last one, the fourth one, what is known as the silicon carbide diodes. The silicon carbide diode. Look here, silicon carbide diode. They have ultra low power loss. Okay. See, Schottky diode has a very low on-state voltage drop. That's what I told you. So therefore, on-state power loss also is low. But silicon carbide diode, it has a ultra low power loss, ultra fast switching behavior, very fast diodes, okay. Highly reliable, no temperature influence on the switching behavior. Okay. Looks like we are achieving almost everything in silicon carbide diode. Okay. Ultra low power loss, ultra fast switching behavior, highly reliable. Then what is the problem? Why are they not very popular? We find only silicon diodes, not silicon carbide diodes. The limitation is they are very expensive. The process is also very expensive. Okay, that summarizes. This coming to the second type of switches, semi-controlled switch. A thyristor or a silicon controlled rectifier. The moment I said semi-controlled device, it has to be a 3-element device. Okay. Anode, cathode and gate. Okay. Anode and cathode, they form the power circuit terminal. They are connected in series in the power circuit. And the gate current is supplied with respect to, or gate signal is applied with respect to the cathode. Say something like this. I have a source, I shown here AC source, a load and a thyristor. So this is the symbol of a thyristor, a diode with a small gate line here. Okay. Anode, cathode and gate. Okay. And can be controlled or can be turned on using a positive gate current, IG. with respect, or control signal is applied with respect to the cathode. Okay. There are 4 layers, say Pn, Pn, okay. And therefore there are 3 junctions, J1, J2, J3. Okay. Pn, Pn, okay. First P is anode, N is cathode, and the gate is connected to this P, okay, this P. This is the gate terminal. N2, or this layer, is very thin and it is highly doped. Okay. This N layer is very thin and it is highly doped. I have called this as P2, or this layer is thicker than this, or thicker than N, and it is less highly doped. Okay. N1 is the thickest of all. This N is the thickest of all and it is less doped. Okay. Highly doped, less highly doped, less doped. Doping level is very low in this, and a very thick layer. And this P is same as this P. Okay. Slightly thicker and less highly doped. Okay. So therefore J3, see, N is very highly doped and a very thin layer. This P is relatively highly doped but slightly thicker. So junction J3 has a very low breakdown voltage in either direction, something similar to base emitter junction in a transistor. Base emitter junction in a transistor is very highly doped, so it cannot block a voltage in either direction. In the sense, it can block a very low voltage. In the class, maybe a small signal diode, you need to apply 0.7 volts to the base to turn it on. And reverse voltage it can block is very low, very small. It cannot block a very high voltage. Okay. So J3, therefore J3 cannot support high reverse voltage, cannot support a very high reverse voltage. Now, what are the various characteristics? When VAK is positive, in other words, the device is forward biased and the current is 0, the device current or the current that is flowing from anode to cathode is very small, the device is said to be in forward blocking mode. Okay, I will repeat. Device should be forward biased, VAK is positive, okay. A very small current is equal to the leakage current will flow through the device, okay. So this mode is known as forward blocking mode. Now what happens in forward blocking mode? There are 3 junctions, J1, J2, J3. I said VAK is positive. So look here, VAK is positive. So P is connected to say positive of the battery, N is negative. So definitely J1 is forward biased and J3 is forward biased. Junction J1 is forward biased, J3 is forward biased, and J2 is reverse biased. Okay. So in the forward blocking mode, junction J2 is reverse biased. Okay. So the entire voltage appears across J2. Okay. Now what happens when the device is in reverse bias mode? When the junction is, when VAK is negative, something similar to the diode, VAK is negative, at that time J1 and J3 are reverse biased. Okay. See, when VAK is positive, J1 and J3 are forward biased and J2 is reverse biased. And when VAK is negative, J1 and J3 are reverse biased and J2 is forward biased. In the forward blocking mode, since J1 and J3 are forward biased, the entire voltage appears across J2, or J2 should block the voltage in the forward blocking mode, remember. Now when the device is in reverse bias mode, J1 and J3 are reverse biased, okay. But I told you that J3 cannot support a high reverse voltage because N2 is very thin and it is highly doped. Okay. So therefore, when it is reverse biased, entire voltage should be blocked by J1. Okay. Now I will show you the characteristics. Okay. Now before that, maybe I will try to show you the two transistor analogy. Okay. See, there are, I told you, there are 4 layers: P1, N1, P2, N2. Now what I will do is, I will cut this and this. Okay. So N1, N1, P2, P2. Okay. Now what is this? Say here, P1, N1 and P2. Now this forms a PNP transistor. PNP transistor. See here, P1, N1 and P2. This is P2. Okay, a PNP transistor. And again here I have N1, P2, N2. It forms a NPN transistor. See here, NPN transistor, NPN transistor. Now how do I interconnect T1 and T2? Base of PNP transistor, say base of T1 is same as collector of T2, NPN. Base of T1 is same as collector of T2. Okay. And collector of T1 is same as the base of T2. Okay. Collector of T1 is same as base of T2, and this is the gate terminal. Gate terminal. So there is a PNP transistor, PNP, a NPN transistor, NPN PN transistor, interconnect them. Okay. Base of PNP is same as the collector of NPN. Okay. Collector of PNP is same as base of NPN. So this is anode, this is cathode, this is gate. And here are the SCR characteristics. I will explain to you now. In the reverse bias mode, characteristics are almost similar to that of a diode, almost similar. Okay. VBR, reverse breakover voltage. Okay. So you should ensure that applied voltage is less than VBR. Okay. Same thing, there I called, for the diode I called as VBD, here I am calling as VBR. Okay. In the forward bias mode, if the current is very small, that is equal to the leakage current, I told you the device is in forward blocking mode, again it is stable, that corresponds to P to Q. Okay. Or P to Q1 or P to Q2. Assume that you are not supplying any gate current. As of now, gate is open. Okay. And the device is forward biased. When the device is forward biased, J1 and J3 are also forward biased. Junction J1 and J3 are forward biased and J2 is reverse biased. So when it is in forward bias mode, the entire voltage J2 blocks. And in case the applied voltage is higher than the breakdown voltage of the junction J2, device goes into conduction mode. I will repeat. There is, I have assumed that gate current is 0. Okay. And if the applied voltage is higher than VBO, see here, VBO with Ig is equal to 0, VBO, that is breakover, okay, forward breakover. What happens? Device goes into conduction mode. But then how does it go in? What is the path that does it take? I told you that just prior to device goes into conduction mode, the voltage is maybe approximately equal to VBO. Okay, it is high. The moment the device goes into conduction mode, the voltage will drop to a very low value. It could be of the order of say 1.5 volts or so, 1.5 to 2 volts. Till 0 to VBO, current that is flowing is very small. It is equal to the forward leakage current. Once the device is in conduction mode, current is limited by the load. Okay. Now, what path does it take? It was blocking a relatively higher voltage. The moment it goes to conduction mode, voltage drops to a very low value. Okay. The path taken by this one is this. I have shown this is to be a dotted one. Why did I show this to be a dotted? Why it is not firm? Like P to Q. Why it is not firm? This is because this region is an unstable region. Why it is unstable? Because it is a negative resistance region. Negative resistance, see, voltages falling, voltage is falling, current is increasing. The slope of this line is negative resistance region, so it is unstable. Okay. And it goes to, see, RS is a forward conduction mode. Current, the operating point here depends only on the load. Okay. And okay, now so there is a third element, what is known as a gate, and therefore by supplying the gate current it should be able to trigger the device. So definitely with the finite gate current, the voltage at which it goes to conduction mode should reduce. Okay. So see, as the gate current increases, the voltage at which device goes into conduction mode also drops. Ig0, so voltage applied should be higher than VBO. Forward breakover, VBO is forward breakover. So with the finite Ig1, device goes into conduction mode at a relatively lower voltage, and if I increase Ig further, see, it goes to conduction mode somewhere at this point. Say PQ for 0 Ig, P1 Q1 for some Ig1 which is less than Ig2, and for that the path is PQ2. And once the device current is higher than the latching current, gate has no control. So I will repeat, by supplying a positive gate current, device goes into conduction mode. Okay. And by supplying a gate current, the voltage at which device goes into conduction mode also reduces. But then the gate signal should be present till the current through the device is higher than the latching current. Okay. The device should be able to latch. Till then gate signal should be present. And having gone into conduction mode, the gate has no control. You can withdraw or you can make Ig is equal to 0. In fact, it is advantageous to make Ig is equal to 0. Why? Gate has no control. If there is a constant Ig is flowing, definitely there is going to be a dissipation in that junction. Okay. So in a way it is an advantageous to make Ig is equal to 0 once the current through the device is higher than the latching. Okay. Because having gone into conduction mode, if the current is higher than the latching, gate has no control, you can withdraw the gate signal. But then to turn the device off, current through the device should fall to a value which is less than the holding current. Okay, somewhere here, see here. IH is the holding current. Okay. So to turn off the device, I will repeat, the current that is flowing through the device should fall to a value which is less than the holding current. How does it happen? We will see whether it happens naturally or do we need to do something different to reduce this current. Okay. We will study during appropriate time, not now. Okay. So that is about the SCR characteristics. This is all the explanation that I am giving. Say VBO is the forward breakover voltage, and this voltage is determined by VBO is determined by J2, because J1 and J3 are they are forward biased. Okay. So VBO is completely blocked by J2. Okay. Now here I have just shown you the plot of the variation of VBO with IG. Okay. See, here is a simple circuit. Okay. I am just closing the switch. Okay. Till the device goes into conduction mode, or till the current through the device, this load current higher than the latching, then I can open the switch. And I am varying this resistor to vary the current that is flowing through the gate circuit. So as Ig increases, the voltage at VBO, so with very low value of Ig is almost the same. This is the voltage. This voltage is determined by junction J2 itself. Okay. After above a certain value, this VBO, or voltage at which device goes into conduction mode, reduces. So it goes on reducing Ig2, Ig3. Okay. Why? It's because Ig, the gate current, it reduces the depletion layer around J2. I'll repeat. The gate current, it reduces the depletion layer around the junction J2. Okay. Now, how do we analyze the process by which the device goes into conduction mode using two transistor analogy? Okay, I just showed you P and PN is equivalent to a two transistor. There is a PNP transistor and there is an NPN transistor, and they are interconnected. Now, using this transistor analogy, can we find out, or is it possible to understand the turn on process of the thyristor? Answer is yes. Okay, I will explain to you now. Come. See, for any transistor, collector current IC is given by alpha into IE plus ICBO. Okay. Collector current IC, IE is the emitter current, alpha is the common base current gain. Okay. Alpha is a common base current gain. It is also approximately equal to IC divided by IE. Okay. And what is ICBO? Is the leakage current of the collector base junction. ICBO is the leakage current of collector base junction. So this is a common equation. IC is equal to alpha into IA plus ICBO. Now for this transistor, T1 transistor, what is IE? Emitter current. Emitter current is nothing but the anode current, IA. Okay. So therefore, IC1 is equal to alpha into IA, because IE is equal to IA plus ICBO1. I am calling ICBO1 is the leakage current of collector to base junction of transistor T1. Okay. Now how about for T2? Now for T2, T2 is a NPN transistor, whereas T1 is a PNP transistor. Okay. IE is equal to IK, the cathode current, IK. So therefore IC2 is equal to alpha 2, the gain of common base current gain of T2, into IK plus ICBO2. Okay. Now we all know that IE, emitter current, is collector current plus IB, base current IB. Now what is IE1? IE1 is equal to IA itself, anode current. Emitter current of T1 is anode current. And what is IB1? Base current of transistor T1. Base current of transistor T1 is same as collector current of T2, IC2. I showed you in the beginning, base of T1 and collector of T2, they are same, they are tied together. So I will add up those two equations. Which are the two equations? These are the two equations, I will add them up. What do I get? IC1 plus IC2 is equal to alpha 1 into IA plus alpha 2 into IK plus ICBO1 plus ICBO2. See, here is that equation I have written. Plus IC2. Now substitute here. IC here is IC1 itself for transistor T1. IB for T1 is IC2. So IC1 plus IC2, IC1 plus IC2 is equal to IA. So these are the two currents, IC1 plus IC2 should be equal to IA, a PNP transistor. So that is equal to alpha 1 into IA plus whatever that equation we are adding to. What about for transistor T2? So listen to me carefully here. What is IE? That is IK itself. It is IB2 base current plus IC2, this current, IB2 plus IC2. Now if there is finite IG, what is base current? Base current is IG plus IC1, okay, IG plus IC1 plus IC2 is equal to I emitter IE2, that is equal to IK. So I will repeat, emitter current of T2 is this current, I base current plus collector current. Now what is base current? You apply KCL at this point for finite IG. IB2 is equal to IC1 plus IG. So therefore cathode current is IC1 plus IG plus IC2. Okay. Now we already found that IC1 plus IC2, IC1 plus IC2 is equal to IA for this transistor. IC1 plus IC2 is equal to IA. So therefore IK is equal to IA plus IG. Okay. Now you substitute this value in this equation. IA is equal to alpha 1 into IA1 plus CBO1 plus this equation. And what do I get? I get this equation. IA is equal to alpha 2 into IG, okay, plus ICBO1 plus ICBO2 divided by 1 minus alpha 1 plus alpha 2. Okay. So, I have an expression here for anode current in terms of gate current, the leakage current of collector to base junction, and common base current gain. Okay. Now, using this expression, how to understand the turn on process of the thyristor, we will do it in our next class. Thank you.